This represents gills of predation. And the fish competition graph is something like that. These are the species of fish in the cove. Here there are two amphipods that are carnivorous. They have no common traits with the other species. Well, some authors say that marine fowl are network with small world structure. And they say that this structure is good for the webs because perturbations are isolated in different blocks. But none of the publications show proofs of the small world structure. So the small world net is fuzzy defined because there are two properties: the characteristic path length, the average number of steps to go from a node to other, and the literature says that it is short. Short is how short, I don't know. And the Oka property is the cluster coefficient, the average, the probability that two nodes connected to a third are connected between them, is high. These are the definitions of the literature: short and high. But how short and how high? Well, we try to answer these questions statistically, comparing values against the values from random webs with the same number of nodes and the same connectivity. We expected that the characteristic path length be lower and the cluster coefficient higher than the corresponding random ones, but with the confidence interval. And in this work made by the group, we compared the empirical values, the real values of different webs in the literature, with simulations for each case with the same number of nodes and the same connectivity. And considering the 99% confidence intervals, we consider that the web have a small world structure if and only if the two conditions are verified together. We use food webs from different oceans and latitudes and different sizes and different connectivities. This is the results. I want to show you two questions. One that is interesting. The distribution degree represents the function of frequency of nodes connection, the number of connection per node, and its frequency. The small world suppose that these distributions could be a power law, but many of these are not power law, uniform log, normal, Poisson. exponential. It's but it's not a necessary condition. It's a condition of small world, but not necessary. Here you can see for each food web the confidence interval for cluster coefficient and characteristic path length. This must be higher for small world situations, and this must be lower for small world situations, but only a fraction of webs have one of the conditions, but only 5 from 28 have the 2 conditions. So a little fraction of webs are really small world webs. The other problem, but is for us the most important problem, is how the web responds to perturbations, because we want to understand if the changes produce or not loss of species, loss of diversity. If we make in silico experiments, for example, experiment of extinction of nodes, the web seems to be robust to extinctions. The loss of species is little. But in the field data, the loss of species is high. So something is not working in the analysis. How about the species traces, the characteristic of nodes?
Sorry, can
Sí.
you explain what it means, the loss of species? What does it mean to lose a species?
In the field, many species are extinct locally by the effect of sediments and by the effect of low salinity. But in the experiments in computational experiments, this not happen.
How do you define extinction in a computational experiment?
A ver, te contesto en español porque si no, no termino más. Uno puede considerar que un nodo se extingue cuando se queda sin ningún nodo que lo alimente, o tomar un umbral, cuando pierde el 25% de las presas o el 50%, y hemos hecho las simulaciones con distintas opciones. The classical approach is consider the network as graph and assume that emergent properties are independent of the nature of the nodes. But our nodes are populations, and populations are complex systems itself. And individuals are complex. They have physiological responses, adaptation, restrictions, evolutive restrictions, etc. The question is if that matters or not. Populations have demographic rates that are not constant, so this have an influence in the dynamic of the web. They have metabolic rates, the speed at which a population processes energy, but this is different for each size of individual, and is not linear with the size of individual. So there are a distribution function of metabolic rate in a population. The density of a population is not constant in space or time, so this have an influence in the dynamic of the system. I show you two examples. The krill is the most important food item for penguins and sea wolf in Potter Cove. But the abundance of krill in 1 month is depend on ice cover in the previous winter and the surface water temperature. Years with high ice cover have high biomass of krill. Years with a little ice cover have little krill, few krill. So if krill is abundant, penguins and sea wolf eat krill and don't eat fish from the coast or fish from the demersal waters. So these populations are higher, and the cormorants are benefited by the krill abundance. So the web is not functioning in the same way depending on the abundance of the population.